In this unit, we will see various commands that can manipulate text at the level of characters, namely, map one set of letters to another or securely encrypt a file's contents. The tr command allows us to map one set of characters into another. In its most simple form, tr takes as arguments a character set to map from and a character set to map to. Here, I map from a space to a dash. This outputs the dash-separated sentence, "This is a test." We can also specify a character range. For example, I map all lowercase letters A to Z to their uppercase A to Z. This converts the sentence to uppercase. Let's now see a more interesting example by revisiting a use we saw when we examined how to access the clipboard. Consider a message you might want to encrypt. Here, I enter "Meet me by the entrance at midnight." To encrypt it, based on the Caesar cipher, I transpose all characters 11 places forward. I also specify the message as input to the tr command. Then, I copy the encrypted message with the T command to a file named secret. T also displays the result on the standard output. We see that the encrypted message is hardly readable. Although such messages are easily decrypted, they are useful in obfuscating things. For instance, participants in news groups use this method to obfuscate hints about movie endings. To decrypt the secret message, I specify the character range in the opposite order. Thus, we get the original message back. The "-d option to tr deletes characters of a specified set. In this case, I delete all vowels. The resulting message contains only consonants and it's just about readable. On the other hand, the "-c option complements the specified character set. Deleting the complement of the vowel set, so all consonants, outputs a message that is even less readable, demonstrating that consonants carry more information than vowels. This may explain why the scripts of all Semitic languages, Arabic, Hebrew, Aramaic, etc., base their writing on them. As an example of using the tr command, let's see what I consider the most amazing demonstration of the power of Unix tools. I'll create a spell checker with Unix commands. First, I fetch from the web a text I want to spell check. Once again, I use the friendly project Gutenberg and download Jane Austen's Pride and Prejudice. The file is named pg1342.txt, but I locally rename it to prideandprejudice.txt. The next step is to convert all non-alphabetic characters into new lines. I run tr complementing the lower and uppercase alphabet set, so anything but A to Z in lower or uppercase is replaced with a new line. As you may have guessed, this command outputs each word on a separate line. All non-alphabetic characters have been removed. Then, I need to convert all uppercase characters into lowercase because my dictionary's words are all in lowercase. I don't want any words with capitals to confuse my spell check. Again, I use the tr command converting AZ uppercase into AZ lowercase. All words are now displayed in lowercase. Next, I remove all duplicate words with a unique command after sorting them alphabetically. This gives us the unique word occurrences of the text. Now, I create a sorted version of my dictionary in order to compare it with the above sorted word list. For that, I use the very efficient com command. I repeat the previous pipeline, piping the unique word list through com-23. I also specify as an argument the sorted dictionary. As you may remember, the -23 option outputs the words that only appear in the first file, in this case, Pride and Prejudice. In this way, we get a word list of potential spelling mistakes. We also see some proper nouns which should be excluded. To do that, I repeat the pipeline, capitalizing with the set command the first letter of each word of the previously resulted list. Then, I repeat the com command to compare again the modified unique list with the dictionary words and exclude the proper nouns. The second set command converts the uppercase letters back to lowercase. In the end, we get a final word list without proper nouns. These words were not matched in any dictionary entry, and thus they probably specify spelling mistakes. In the words of the famous computer scientist Andrew Tannenbaum, the nice thing about standards is that there are so many to choose from. This is unfortunately the case in the standards employed to encode character representations. In this area, there are many incompatible standards for diverse character sets, such as those containing the characters of Asian, Cyrillic, or Greek writing systems. Recode is a command line tool that allows us to map between those character sets. To see an example, consider this verse from Goethe's Faust play. Notice how some characters, like the one after the first space, or another in the middle of the third line, appear incorrectly. These are not text errors. They denote encoding incompatibility. Running the file command on the text file, we see that it's encoded with the ISO 8859 standard. This means that Roman characters of non-English languages, such as German or French, are encoded in the second 128 positions of the character set. Unfortunately, this 8-bit standard can't work for all languages, because with only 256 possible encodings, there are not enough positions in the set to encode all characters. Nowadays, we use a different encoding standard named Unicode, which has enough space for all characters. That's the encoding I also use in the video you're watching. As a result, the different standard used in the file is the reason we cannot see it properly. Looking at the file with the OD command, we see that the fifth character, which appears incorrectly, has the octal value 304. This means that a single byte is used to encode the character A with an umlaut mark. That's the character that doesn't appear correctly in this case. With the recode command, we can change the encoding. I specify that I want to recode from ISO 8859-1 to UTF-8, saving the output to a different file named Faust UTF-8.txt. UTF-8 is a variable length encoding for representing Unicode characters. Now, running file on Faust UTF-8.txt, we verify that it indeed contains UTF-8 Unicode text with carriage return line feed line terminators. Looking again at the file at the byte level, we see that the fifth character is encoded with 2 bytes. That's how UTF-8 works. For the subset of English characters, which are included in the first 128 positions of the character set, UTF-8 uses 1 byte to encode them, whereas the remaining characters are encoded with 2 or more bytes. Let's now look at the recorded file. We see that it appears correctly. Der Äpfelchen appears with the German umlaut A character. Also, on the third line, there is now the word Fühl, which has an umlaut U. From UTF-8, we can now recode back to ASCII. The characters that could not be represented before in the ASCII character set, with the first 128 characters, are now represented as 2 characters. Umlaut A is represented by a double quote mark followed by A. Similar for umlaut U. There are different ways to represent Unicode text. Apart from UTF-8, there is also UTF-16, where most characters are represented by 2 byte values. Let's recode the UTF-8 file into UTF-16. Running file on the output, we verify that it is UTF-16 and specifically big endian. This specifies the order of bytes representing each character. Finally, running OD on the file to see its contents, we see that there are no visible ASCII characters now. Instead, each character is represented by a 2-byte pair. If you want to employ industrial strength encryption, use the OpenSSL command rather than TR, which we saw earlier on. Let's use TR to obfuscate the contents of the book Pride and Prejudice by rotating all characters 11 places forward. In this way, they are not trivially read. Let's now look at the characters' frequencies. I write a shell function named frec. This takes each letter as input and places it on a separate line through the sed command. Sed substitutes dot, so any character, with the same character, denoted by ampersand, followed by a new line. This is a global substitution, note the G. The output is then sorted and piped to unique -c to count each letter's occurrence frequency. Finally, I sort the frequencies in reverse numerical order and print with head the first ones. Let's now get a second novel from the web. Here I choose The Brothers Karamazov by Fyodor Dostoevsky, which I save in a file named karamazov.txt. I run frequency function on this file by typing the function name frec and the file name. We get the characters' frequency distribution. This depicts a notable variation among the characters. The space character is the most frequent, followed by E, followed by T, O, A, and so on. Running frequency on the secret file of Pride and Prejudice, we observe a similar distribution but with different letters. Again, space is at the top, then comes P, then E, L, and so on. By mapping between the two frequency distributions, we can make an educated guess regarding which character has replaced which. In this way, we may be able to decode the file. Now comes the question, how can we obtain real secrecy? In this case, the OpenSSL command is the solution. As an example, I run OpenSSL encrypting with an algorithm called Advanced Encryption Standard, AES. I use a key of 256 bits and chain together the blocks using a technique called cipher block chaining. This means that each block is encrypted based on the preceding one and prevents some types of attacks. I specify as input file prideandprejudice.txt and create a real secret file. Next, I enter a password. Let's now look at the distribution of the real secrecy file. We observe that all characters have similar frequency now. This indicates that the file has been encrypted with a strong algorithm rather than a toy algorithm as is the Caesar cipher. To decrypt the real secret file, I run OpenSSL on it, specifying enc-d for decryption. I also need to enter a password. In this way, we get back the original contents. This concludes our unit on processing character data. Stay with us.